In this lesson, we're going to be looking at our exponential functions, and we're going to look at how to graph our exponential functions and what we actually mean by an exponential function. So the first thing that we want to do is to look at our definition of what we mean by an exponential function. And if its exponential function is written in the form of f of x equals b to the x or y equals b to the x, where b is a positive constant other than 1. Now another way that that could be written is where b is greater than 0, that means it's positive, and it doesn't equal 1. So we're not going to be talking about raising 1 to a power. We're not going to be talking about raising a negative number to a power. And x is any real number. Our exponent can be anything. But our base has to be a positive number, and it cannot be 1. So some examples of exponential functions that we could look at. We could have f of x is equal to 2 to the x. We could have y is equal to 3 to the x plus 1. These would all be exponential functions. The main thing about an exponential function is that your variable is in the exponent. Now, if you remember, we called this number the base and this number the exponent. And it's important that you do know how to name these and what the parts are called. We could have another one. We could have g of x is equal to 1/2 to the x minus 1. In this case, our base is 1/2, and our exponent is x minus 1. Some things that would not be an exponential function, y equals x squared. That's not an exponential function because our variable is not in the exponent. Another one would be g of x equals 1 to the x. This would not be an exponential function because our base is 1. And our base cannot be 1. Or if we had h to the x, or h of x is equal to negative 2 raised to the x, that would not be an exponential function because our base is a negative number. All right, we want to look at actually evaluating some of our exponential functions, and we'll look at it. And doing this, we will have to use a calculator. A long time ago, we actually used what were called, we used some log tables, which we will get into logarithms, and we use those to do this evaluation. But now we will use a calculator to do that. You're a lot more likely to have a calculator than a log table. So let's look at this value. All right, we're going to pull up our calculator, and we're going to look at how to find this on the calculator. Now our problem was y equals 3 to the 2.4. So to evaluate that, we would take our calculator and we would have 3, and then we have our raised to the power 2.4, or 2 4/10 would be the correct way of reading that. Press enter, so that would equal 13.9666117. Now we're going to round these off to 3 decimal places. So we have our 1, 2, 3. Now we decide, does this stay a 6 or round to be a 7? Since the next number is greater than 5, that would round to be 7. So that would be 13. 0.967. Okay, if we had y is equal to 5 raised to the square root of 3. Well, we want to do this one on the calculator. So let's pull it up. And I wanted to just make that just a little bit smaller so that we could move it over and see the problem. There we go. Okay, we want 5. Now, in this case, the way that we do our raise to, again, we'll use the up arrow, but our exponent's a square root. So we'll do our second square root of 3. Now, because it opened parentheses under the radical, we need to close them. And so that would be 16.242. If we had as our problem, we'll just go ahead and write that down. That was 16.242. If we had y is equal to 6 to the negative 1.2. Now we can have negative exponents, we just aren't dealing with negative bases. And so this would be 6 raised to the negative 1.2. So rounded to 3 decimal places, this would stay a 6, so we would have 116 thousandths. So 116 thousandths. And then if we had y is equal to e to the 3.4. E is a number that occurs in many situations. It was a number that occurred so often that they gave it a special notation and called it E. We deal with it a lot in our logarithms, especially when we're dealing with what we call constant logs. And E is an irrational number. It's kind of along the line that we use pi to represent 3.14. Well, we use E for a specific representation. E approximately has the value rounded off, so we can make those wavies 2.718. But it's something that occurs kind of naturally as you're going through doing some things, and so we've given it a specific name or a symbol instead of putting down the 2.718, the number that keeps going, then we just call it E. Now, the way that we use this on our calculator, you'll notice that right here above this button that's called LN is e to the x. So that's what we're going to press. It automatically puts, we'll press it second since it's above the key, and notice it put e raised to a power, and we want to raise it to the 3.4 power. And so that turns out to be 29.964, or 29 and 964 thousandths. So we should be able to evaluate exponents. Now, there's several ways that we're going to have of graphing. You'll either be making a table or you'll be using transformations. And sometimes it's just nice to go ahead and make the table as we go through and work these. So we're going to do some problems where we make a table and then we will graph them. So let's say that we want to graph y equals 3 to the x. Now in this case, as we make our table, we're picking values for x, and I'm going to pick -2, -1, 0, 1, 2, values that are close to the origin. So I'm going to have 3 to the -2. Well, if you remember, a negative exponent means we want the reciprocal, or 1 over 3 squared, which is 1/9. 3 to the -1 would be 1/3. 3 to the 0 is 1. 3 to the first is 3, and 3 squared is 9. Now, if we graph those, we've got our points: -2, 1/9, -1, 1/3, 0, 1, 1, 3, and 2, 9. Now you can see our numbers get very small, and as we went out uh, more negative, then we would have numbers that get closer and closer to 0. Our numbers get big very rapidly. This is one of the things, characteristics of an exponential function, is your values will get big very quickly. And or increase exponentially. You'll hear that term quite a bit. Now notice that we approach 0, but again, if 3 is our base, this was y equals 3 to the x, we can never have 0. If you've got a base, a number, even if your exponent's 0, that's going to equal 1. And so we will get close to 0, but we would never be 0. Now let's make another table, and I'll make it here on the graph where we can see it. We're going to plot our points. Let me just make it a different color so that we'll know which one goes with which. And let's graph y equals 1/3 x. Well, we're going to pick -2, -1, 0, 1, 2. Okay, if we have 1/3 raised to the -2, well, we want the reciprocal of our base. The reciprocal of 1/3 is 3, so this is 3 squared, or 9. If we had 1/3 raised to the -1, we want the reciprocal, so that would be 3. 1/3 raised to the 0 is 1. 1/3 to the first is 1/3, and 1/3 squared is 1/9. So if we graph this one, when x is -2, y is 9. When x is -1, y is 3, 0, 1. Then we have 1/3 and 1/9. And again, we're going to be coming down or decreasing. And then our x-axis acts as a horizontal asymptote. All that we did here was change our base. Here our base, for the black one, our base was 3. Here it was 1/3. Another way we could have written this second graph that we did, we could have written that equation as y equals 3 to the -x. Remember, a negative exponent says we want the reciprocal of the base, so that would be the same as the 1/3 x. And so we have our graphs. Now, we've got some specific characteristics of these that we're going to look at. First of all, for either one of these graphs, for the red or the black one, our domain was -infinity to +infinity. That's going to be true of every exponential function. Your domain will be -infinity to +infinity. The range, since this was an asymptote, our range was 0 to +infinity. That's also true for exponential functions. Now notice both of these, the graph went through the point 0, 1. That will always be true because no matter what your number is, any number raised to the 0 power is 1. So when our exponent is 0, then we're going to have a value of 1. This one was b was greater than 1. And notice our graph was increasing. When b was less than 1, but still a positive, it has to be a positive number. So it was between 0 and 1. Notice our graph is decreasing. And we could look at these. This would be a one-to-one function because this is a function and its inverse is also a function. And then our y-axis is a horizontal asymptote. Now these things are going to be true for any of our exponential graphs. The domain will be -infinity to infinity. The range is 0 to infinity. It's going to go through the point 0, 1. If your base is greater than 1, your graph is going to be increasing. It's going to be going up as it goes to the right. If your base is between 0 and 1, then the graph goes up to the left. But as we look at our graph, it would be decreasing. These functions will be 1 to 1, and the horizontal asymptote will be the x-axis will be a horizontal asymptote. Now, because of some of these characteristics, then we could go through and actually use some of our transformations. We won't spend a lot of time graphing these by transformations, but it does work out as we go through, and it makes our graphs just a little bit easier, especially because of these characteristics. So let's just look at a few as we go through to graph them. Now, all those things that we talked about earlier in transformations are going to be true in these graphs. So let's start out with the graph, and we just did it, but let's go ahead and look at it a little differently. Let's say that we have y is equal to 3 to the x plus 1. Now, we graphed y equals 3 to the x. When we graphed y is equal to 3 to the x, we had 1/9, 1/3, 1, 3, and 9. So you would have to find your points for the parent function of your base. So that's the graph that we started with. I am having trouble going through that 0.29. But that would be our graph. Now, if you remember back when we were doing our transformations, the value that was with the x, it was understood to be in parentheses, and we would undo this. And so what this does is it causes our graph to move left or right. We would undo it by subtracting 1, so our value would go, all of our points would go to the left 1. So we would have our 1/9 there, our 1/3 here, 1, 3, and 9. And so it's typically the same graph. We just shifted everything over 1 unit. Now that means we didn't cross our y-axis anymore at y equals 1. We crossed it at y equals 3 as we went through that part. Okay, let's take this one. I'm just going to leave those up there. And let's do the equation y is equal to 3x plus 2. Now, if you remember what this number does is it moves it up or down. Since it's a positive, it's going to move all of our points up 2. So there would be 1, 2, 1, 2. And I'm going from I should be going from the black graph because that was our parent function. So let me go back. I would have 1, 2, 1, 2, 1, 2, 1, 2, and 1, 2. And in this case, y equals 2 is our asymptote. So what you would have to do is get the points for the parent function, and that's going to change depending upon what your base is. Most of the time our bases are fairly small. And then you would just go through the same transformations that we did with all of our other transformations. The numbers in the parentheses, they move your y value, they move your x value, and you undo it. The numbers outside, they move your y values, and you do those. Now, let's just go through and look at a couple of other graphs. And in these, we may pick some points again as we go through to look at them. Let's say we've got y is equal to 2 times 3 to the x. Well, in fact, I could have just left that up there that we had. We're still going to do this by transformation. Okay, that was our mother, the parent function. Now, what this number does is it causes all of your y values to double. It causes everything to go up twice as fast. And that would be the same as the a of our other functions when we were doing our parabolas and our absolute values. That just meant that we took whatever our y value was and we multiplied it by 2. So we have 1/9 multiplying that by 2 would be 2/9. 1/3 times 2 would be 2/3. 1 times 2 would be 2. 3 times 2 would be 6. And 9 times 2 would be 18. So what that does is it causes this to increase a lot faster. It does a stretching. If we had as our function well, let's do this one. And we did it a while ago, but let's do it as a transformation. Y equals 3 to the negative x. Now, if you remember when we negated the x, we reflected it across the y-axis. When we negated the y, we reflected it across the x-axis. So that means we're going to take all of these points that we have in red and we're going to reflect them across the y-axis. So that was at 1/9. This one was at 1/3. That one's on the axis. This one's at 1 and then at 2. And we would have our function. But it's just reflecting it. And so it's going back through a lot of those same things that we did before. Let's say we have y is equal to -2 times 3x. Well, what this does is it not only doubles our points, but then it reflects it across the x-axis. So if we were going to graph that one, okay, we had 1/9, and multiplying that by -2 would be -2/9. 1/3 times 2 would be -2/3. 1 times -2 would be -2. 3 times -2 would be -6. And then 9 times -2, we would be way down here. I'm just having a little trouble getting through those points. Let's see if I can do just a little better. There we go. And then it would go down a lot steeper. So you can graph by using your transformations. Let's look at one final graph, and this is graphing y equals e to the x. Now to do these, we can use our calculator. We can also make a table and use our calculator. And let's do -2, -1, 0, 1, 2. Now, we know that any number raised to the 0 power is 1. And this is going to be e, which we said was 2.7 18. So we could have that as 2.72. That would possibly be a good, just round it off. We have e squared, and so that turns out to be 7.39. You can use your calculator to get these points. E to the -1 would be 0.37, and e to the -2, 0.14. Notice, no matter what our exponent is, our final answer is going to be positive because we have a positive base. And if your base is positive, which that was one of our stipulations, then your answer will always be positive. So if we graph these points, we have negative 2.14, negative 1.37. We still cross the y-axis at 1, then 2.72, and 7.39. 2, 4, 6, 7, about here. And so we have our exponential graph. Now, one of our uses, and what you're going to need to be able to do is just to graph some of these. But then we use a lot of this, especially when we get into problems that deal with compound interest. And especially that's one time that you might see the E, or we end up doing some problems with exponents. So let's just look at some problems. We're going to deal with two formulas. One is our formula for compound interest, which is A is equal to the principal times 1 plus the rate divided by your number of compoundings raised to the nt, the number of compoundings, times your time in years. Now, when we do interest, what y'all may be used to is the formula that I equals PRT, where P is the principal, the amount of money you invested, R is your rate, and T is your time. This is what we call simple interest. And what happens with simple interest, you put your money in the account, and when you go to draw it out, which may be 15 years later, then they will figure the interest on it, and they will give you back the money you put in plus the interest. Now, what happens with compound interest is they figure that interest as we go along. We may compound it quarterly, semi-annually, monthly. There's even what we call a continuous compounding. And what they do there is, if it's quarterly, then every 3 months they will figure up how much interest you earned on that account. They will then take that interest and add it to your principal. So the next month, when they figure your interest, you have a different principal. You had what you put in plus how much interest they paid you that first month. And so they're paying you interest on interest, and your amount will grow much faster. Now we're going to look at a problem or two and just see the effect of compound interest. Let's say that you wanted to invest $5,000 for 10 years, and we're going to do it at 6.5% interest. Well, the first bank you go to is going to pay your interest semi-annually. That means twice a year. And so you want to know, well, how much money would I have earned? So we would use our formula. Now in this, A stands for the accumulated amount. That's how much you put in plus how much interest you earned on it. Well, we're going to invest $5,000 times 1 plus the rate, which would be 0.065, we'll change it to a decimal, divided by our number of compoundings. If it's done semi-annually, then it's done twice every year. Raised to the 2, the number of compoundings, times the number of years that you left it in. So that meant we compounded this a total of 20 times. So we've got 5,000 times 1 plus 0.065 over 2 raised to the 20. Now we can do all of that on the calculator. We don't have to stop and break it up into parts. So let's look at our calculator and let's clear this out. So we're going to invest $5,000. Then it's going to be parentheses 1 plus Okay, 0.065 divided by 2. Now our order of operations tell us it's going to do that division before it adds, which we wanted it to do. Okay, raised to, now it was going to be 2 times 10. So you either have to put that in parentheses, parentheses 2 times 10, or you can just say, well, 2 times 10 is 20, and put down the 20. And then press enter. So if we invested $5,000 at 6.5 interest compounded semi-annually for 10 years, then at the end of the 10 years, we would have $9,479.19. Now, since we invested $5,000, then that would mean that $4,479.19 was how much interest we earned on that investment. Okay, let's take a different one. And let me go ahead and write this answer down. So this turned out to be $9,479.19. Okay, let's do this same one, but let's do it quarterly. Quarterly is 4 times a year. So it would be our accumulated amount is how much we invested times 1 plus our interest rate, which is 0.065, divided by our number of compoundings. Well, that would be 4 raised to the 4 times 10. Now, if we go back to our calculator, notice a lot of that's the same as what we just put in, but we need to change how many times it was compounded and what we raise it to. So if we'll go to our calculator and press second and then enter, what it does, it brings up that last problem. And we can just go back in there. You can back arrow. Oops. And we're going to make that a 4 because we're compounding it quarterly. And we're going to go here and make that a 4. And so we don't have to type so much in. And notice we made a little bit more money when it was compounded quarterly because we had more compoundings. So we would actually make on that one $9,527.79. Okay, let's look at it where it was compounded monthly. So A is equal to 5,000 times 1 plus 0.065 divided by 12. If it's done monthly, then it would be done 12 times a year, raised to the 12 times 10. So since we left it in 10 years, then we're actually getting 120 compoundings. If we go to our calculator to put that in, well, again, we can do second, enter. It brings that last one up. And it appears that we've frozen. So let's just, okay, we're going to put in our 5,000. We kind of had to start over since our calculator froze up. Then 1 plus 0.065 divided by 12, since there's 12 months in the year. Close the parentheses, raise 2. Now, here we're going to put in our 12 times 10, or 120. If you get to ones that you don't know what they multiply to be, then it's okay to go ahead and put that, as long as you put it in parentheses, 12 times 10. So on that one, we would make $9,560. So we keep making just a little bit more. Okay, the last one we want to look at is where it was compounded continuously. That means all the time. And if we go back to the very start, when we were looking at our formulas, we have another formula. It's A equals the principal times e raised to the RT. This is our formula for continuous compounding. It's a little bit different, but we will use it then for this last problem that we're going to look at. So that would be A, the accumulated amount would be 5,000 times 1 plus 0.065. Excuse me, we're not going to use that formula. We're using our continuous one, which is A is equal to our principal, 5,000, times E raised to the NT. Now, N was the number, it was raised to the PT, how much our interest rate was, times the number of years that we're going to leave it in there. So that's going to be 5,000 E, we would move our decimal point, 0.65. And if we go through and we get that value, so 5,000 times, okay, it's E raised to, and I keep trying to put in too many zeros. Now, you on your calculator for your E, you have to do second and then that LN button. And so raised to the 0.65. And so that tells us we would get $9,577. And so again, we get just a little bit more. So the more times that you can have something compounded, the more money you're going to make. And you'll make more money than if you put it into simple interest in an account in simple interest. So this is just an introduction to to exponential functions, what they look like, what their graphs look like, the characteristics of their graphs, and then using some of our interest formulas to get amounts.